So first of all, I've drawn the circuit a little bit differently than given in the problem because this was a little bit easier for me to understand and visualize. I've also written down some of the information that was given in the problem already. So we know that Q1 and Q2 are in the saturation region. This current here, requires a minimum 0.5 volt voltage drop across it to operate properly, and both Q1 and Q2 are NMOS as well as matched, which means that VOV equals VGS minus VT. So for the first part, for circuit A, V in is equal to 0 volts, and we have to find all of these values. First of all, since we know that Q1 and Q2 are in the saturation region, this is all true, so VDS has to be greater than VOV. VOV is greater than 0, and we know the equation to find ID. And using that and the KCL at this node here, we see that I is equal to ID1 plus ID2, and we know that I is already equal to 200 microamps. We can also see from this node, looking at voltages, that VGS1 is equal to VGS2, and then also these two values are equal to negative V3. And we know this because this equation here with Vi minus Vgs equals negative V3, and Vn is 0. And so that's how we get these three values equal to each other. And so using that KCL from before, we plug in all of the values given to find ID1 as well as ID2, which should all equal, when added together, 200 microamps. And we know that VGS2 is equal to VGS1. So that means that ID1 and ID2 are actually equal to each other. And so we can simplify this into this equation: 2 times 0.5 times 1.6 microamps over V squared times VOV squared, which should all equal to 200 microamps. And solving for VOV, we get that it's equal to 0.3535 volts. And from there, using this equation, we can get VGS1 and VGS2, which are equal to 0.8535 volts. And then from there, using this equation, we can find V3, which is equal to negative 0.8535 volts, as well as get I, which you can either just divide 200 microamps by 2 or plug in the values that we got before. And then we can also find VD by using this portion of the circuit up here and seeing that 2.5 volts minus 20k times ID equals VD. And so solving that for VD by plugging in the ID value from here, we get that VD is equal to 0.5 volts. Moving on to part 2, Vin is now 1 volt. So only Vin has changed, which means that VOV is the same, VGS is the same, and ID is the same, as well as VD. So the only value that is changed is V3 as well as VDS. From before, I've calculated the VDS value, which we can find simply by using VD subtract V3, then we get VDS. And so to calculate V3, we use the new Vin minus VGS, plug in Vin, and our new V3 value is 0.1465 volts. And for our new VDS, again using VD minus V3, we get VDS is equal to 0.354 volts. And for part 3, it's very similar to the last part, with Vn now equals negative 0.4 volts. And so we only have to calculate a new V3 and VDS. So V3 is equal to the new Vn minus VOV, which is equal to negative 1.254 volts. I'm sorry, not VOV, but V3 equals Vn minus VGS, so that's negative 0.4 volts minus 0.854 volts, and that equals negative 1.254 volts. VOV stays the same. And VDS now equals VD, so 0.5 volts minus this new V3, which equals to 1.754 volts. And so for part 4, we look at what is the highest Vin so that the circuit operates properly. And so first I wrote down some equations about the conditions that have to be satisfied for this circuit to operate properly. So one is that the voltage drop across the current source must be greater than or equal to 0.5 volts. So this voltage drop is over the current source is equal to V3 minus negative 2.5 volts. We can see that here with this V3 node minus negative 2.5 volts gets us that voltage drop. And the other thing that has to be satisfied is that Q1 and Q2 are in saturation. So VOV has to be greater than 0, VDS has to be greater than equal to VOV, and we know this ID equation. So this VDS greater than or equal to VOV is the important part we're looking at. And so as VI, using the values before from parts 1 through 3, I wrote down here that as Vi increases, V3 increases and VDS decreases, but as Vi decreases, V3 decreases and VDS increases. So for this problem, VDS is the limiting factor when Vi is increased. And so using that, VDS has to be greater than or equal to VOV, which we saw for all three parts. VOV is equal to 0.354 volts. And so how we calculated VDS in, again, those three parts before was looking at VD minus V3. VD stays the same for all problems, so that's 0.5 volts. And we subtract V3, which is equal to Vn minus VGS. And again, VGS stays the same here, which is at 0.854 volts. So plugging that all in, we get this equation has to be greater than or equal to VOV, this 0.354 volts. And solving for Vn, we can see that we get this Vn has to be less than or equal to 1 volt. So for part 5, we do something similar, but now instead of VDS being the limiting factor, V3 is the limiting factor as we decrease Vi. And so using the equation from above, this V3 minus negative 2.5 has to be greater than 0.5 volts. Again, this is the voltage drop over that current source. We find V3 by taking Vn and subtracting VGS and plugging that in and the values for VGS, we get that Vn has to be greater than or equal to negative 1.147 volts. So for circuit B, again, I drew this a little bit differently than given, but we're just looking at this portion, really. So we're looking for VOV and all of these other values for Q4. So we know that both of these are NMOS, again, so that means VOV equals VGS minus VT. We know the value for ID3, this is 200 microamps here through Q3. And we know that it's in saturation, and so we know the equation and we can solve for VOV3, which equals 0.5 volts. That gives us VGS3 because of VOV equals VGS minus VT, so that's 1 volt. That means that VD here has to be equal to negative 2.5 volts plus VGS3, and that gives us negative 1.5 volts. And using all of those values, we can find VGS4 and VDS4 because we know the voltage at VD as well as this VSS is negative 2.5 volts. So we get both of those values, and we can also calculate that ID4 is going to be equal to this equation, plug in VOV, and we see that ID4 is going to be equal to 200 microamps, same as what is going through Q3. And these values are as expected because Q4 and Q3 are matched with each other in both NMOS in saturation. So for the last value, to find R, it's pretty easy. We just plug in what we found before and use this KVL of 2.5 volts minus VD equals ID4 times R. And so plugging in all those values that we found before,
we see that R is equal to 20 kiloohms.